Have you ever seen a long string of ones and zeros at first glance? It looks like complete gibberish, but to a microprocessor, this is just another number. You see, computers don't store decimals the way we write them down. They rely on a universal language called the IEEE 754 floating point standard. This standard is what helps every computer, from the phone in your pocket to massive supercomputers, represent and interpret real numbers consistently. Today, we're going to decode one of these mysterious binary patterns and discover how a computer converts it back into the decimal numbers we use every single day. The IEEE 754 single precision format uses 32 bits to represent a real number, and it's divided into three distinct parts. First is the sign bit, which is the very first bit. It simply tells us whether the number is positive or negative. A 0 means it's positive, and A1 means it's negative. Next up, we have the exponent. These are the next 8 bits, and they control the scale or magnitude of the number. Think of it as controlling whether the number is really big or really small. Finally, we have the mantissa, which is the last 23 bits. This part holds the detailed fractional information that gives the number its precision. To decode an IEEE number into decimal, we use this simple but incredibly powerful formula. -1 to the power of the sign bit, times 1 point the mantissa, times 2 to the power of the exponent minus 127. That 127 is called the bias, and it has a clever trick that allows the exponent to represent both positive and negative powers of 2. This is essential for handling both tiny fractions and massive values. Now, let's walk through a real example together. We'll decode this IEEE 754 number. 10,010,100,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000. First, let's break it down. The sign bit is 0, which means our number is positive. The exponent is 10,000,010, which in decimal is 130, and the mantissa is 100,011, followed by a bunch of zeros. Step 2 is to adjust the exponent. We take our exponent value of 130 and subtract the bias of 127, which gives us 3. For step 3, we rebuild the mantissa. We always assume there's a leading one before the binary point, giving us 1.10011 in binary. Now let's convert that fractional binary part to decimal. The binary number 1.10011 is equal to 1 plus 1/2 plus 1/16 plus 1/32. Adding those up, we get 1.59375. Finally, step 4 is to apply the formula. We have positive 1 times our mantissa value of 1.59375 times 2 to the power of 3. This simplifies to 1.59375 times 8, which equals 12.75. So that long binary sequence actually represents the decimal number 12.75. So what just happened here? We took a stream of bits, something that looks like total nonsense, and revealed a meaningful, precise number. This is exactly how your calculator, computer, or even your smartphone interprets floating point numbers when it performs calculations. Behind every decimal you type, the microprocessor is silently translating it to the IEEE format and back again, billions of times per second. If you found this breakdown helpful, be sure to like this video and subscribe for more deep dives into how technology works. Thanks for watching.